The most powerful AI chip on Earth, assembling itself piece by piece. 40 grand, if you can get one. The B300, the king. So let's tear it apart, layer by layer. First, the heatsink comes off, a solid block of machined aluminum. Under it, a copper vapor chamber, spreading 1400 watts of heat. Between the metal and the silicon sits a layer nobody talks about, thermal paste. A few grams of gray compound. Remove it, and this $40,000 card cooks itself in seconds. Flip the card over. The back is armor, a machined plate that keeps the board from bending under the cooler's clamping force. The board itself is a sandwich, copper and fiberglass, signals on the surface, power flowing through buried planes inside. And around the edges, the power delivery army. Dozens of converters, stepping the incoming voltage down to roughly 1 volt, at more than 1,000 amps. 1,000 amps. That's arc welder territory, flowing silently a millimeter under your fingertips. These dark blocks are capacitors, microscopic batteries, smoothing every hiccup in that flow. This edge is how it talks to the world, the SXM socket. Power in, data out, no cables anywhere. And then this. This is the part NVIDIA doesn't want you to think too hard about. That's not one chip. It's two. Two giant dies, each printed at the absolute size limit of the machine that makes them. TSMC's lithography tools physically cannot print anything bigger. So NVIDIA fused two maximum-sized dies together. The bridge between them moves 10 terabytes per second. That's fast enough that the two halves genuinely behave like one brain. Under a microscope, the surface looks like a city because functionally, it is one. Streets of interconnect, districts of compute, a subway system moving data underneath. And all of it sits on a substrate, a miniature circuit board of its own, translating microscopic wiring out to the board's world. The most expensive thing on this $40,000 card isn't the GPU. It's these 8 towers of memory, surrounding the dies like bodyguards. Each tower is 12 silicon dies, stacked vertically and wired straight through. That's 96 memory dies on one card. 288 gigabytes, moving 8 terabytes every second. Each tower talks to the GPU through more than 1,000 microscopic wires, drilled straight down through the silicon. That's why it's called high bandwidth memory. The highway is 1,000 lanes wide. That's not cheating. Modern AI genuinely runs on these tiny numbers. But when you hear 7.5 times faster than Hopper, that's part of the trick. So how do you even build something like this? It starts in Taiwan, at TSMC, on a wafer of silicon the size of a dinner plate. Then comes the step almost nobody talks about, packaging. 2 compute dies and 8 memory towers, all placed onto one silicon base, joined by microscopic wiring. The process is called CoWoS, and it is the single biggest bottleneck in the entire AI industry. TSMC's packaging lines are sold out, completely. NVIDIA alone locked up roughly 60% of the world's capacity. 1,400 watts. One card. That's a microwave oven, running at full power, 24 hours a day. Air can't cool this anymore. Liquid flows directly across the chip through a cold plate. 90% of the heat leaves as warm water. The cold plate sits millimeters above the silicon, a maze of tiny channels carved into copper. And that warm water out the other side? Some data centers now use it to heat nearby buildings. Here's the secret. This was never the real product. The real product, 2 B300s and a CPU on one board. 2 boards to a tray, 18 trays to a rack. 72 GPUs, wired as one giant chip, 130 terabytes a second. Behind them, a spine of solid copper. One cabinet, $3 to $4 million. And data centers order them by the hundred. Rubin is next. We'll tear that one apart too.